Hello and welcome in this first tutorial about the new features of Midas NFX 2015. So in this tutorial we'll talk about particle CFD and we'll simulate a 2D axisymmetric model. So I choose axisymmetric CFD and the unit will be in meter. So let's click on OK. So now let's build the model. So the model will be an inertial impactor. So it's a very famous problem and probably you will recognize it. So let's create some points on the grid that will represent the boundary. So I can just click on the right points like that to create. So one point here, here, to create the area. Now that I did that, I can just connect these points with the polyline. So be sure that in the snap the point is selected. And I just created a face for my CFD model. Now the second step is to create some material and then mesh all that. So let's go into Material tab and let's create a fluid CFD material, which will be air material, and click on OK. Now let's add a property, so 2D property CFD, which will be associated with air, so I can change the name to air and click on OK. Now I'm ready to mesh the model, so I go in 2D mesh, I select that, and the size will be 0.01 meter. Let's do the preview, looks okay. Okay, now I meshed my model. Now the next step is to assign the boundary condition which is required for the CFD and the particle analysis. So let's assign the inlet first. So inlet is here and the speed will be 0.01, the velocity will be 0.01 meter per second and a pressure outlet of 0. Okay. Now I have to create the wall condition, so let's go to wall and select first those wall here. So you see I selected this one, this and this one. So those wall are the no slip wall, and the particle will basically bounce against this wall, so we'll choose specular as a type of the particle wall type. So this is new, you see this has been added, and this basically defines the behavior of the particles on this specific wall. Let's click on apply. Now this wall here is a bit different because the particle will be able to deposit on this, not bounce, so it will be deposition type of wall. So apply, and this wall here on the side is axisymmetric wall. So we have, when you select here, it will be none, so there will be no wall because it's axisymmetric, but for the particle it will be specular to simulate that the particle will be able to enter from this side as a symmetry. And now I have my boundary conditions. Now that the CFD model itself is defined, what we'll have to define is the particle distribution. So particle distribution represents the area where the particle will appear at the beginning of the analysis. So you have to tap simple and advanced. So I'll use a simple, and first of all we'll have to define the particle properties through the particle manager. So you see that you have several types of materials that you can use for the particle. So for this example we use simple glass particles, and we'll use 1,000 particles, and this is the initial distribution, so 0.39, and here 0, 1, 0, 4, and 0. And if you look on the preview, yeah, it will be something like that. So which means that in X it's a bit smaller, so it should be 0, 2. Yep, now I have it in all this area. If you want to increase, let's say the Y, so if you put 36 for example, you see that the area will increase like that. Now the sphere radius, this is the mean radius of each particle, and the initial velocity, so let's input minus 0.01. Okay, and now I define this particle first distribution. Now everything is ready for the simulation, so the only thing we have to do is to create a CFD analysis case. So in this case we'll do a steady state CFD analysis, and let's set up the analysis case. So this will be laminar analysis, so we'll set the turbulence model to laminar. Regarding number of step, 1,000 step would be enough, I think, to reach the steady state, so we'll leave it like that and click on OK. So now we just have to run the simulation, so let's click here and solve. The solver will start to solve the problem, and we'll have to wait a few seconds. So as you see, this is quite fast. So you have the result here in the text output window. You can view if it's converged, and if you don't want to wait until the end to see the first result, you can directly go here, right click, and you have this new function called reload the result file. If you click here, it will directly display the first computed result. So this is it at step increment 51, and as you see it's already finished. Now this is the final velocity distribution at the steady state and the final pressure distribution. Now what you maybe think is that there's no particle here, and the reason for that is that I chose to compute separately the flow and the particle. So you can do it in once, and in this case if you compute the particle along with the flow, you can directly have the results of the particle here. But what I'll do is I will create another steady state case, and I'll show you why. What I will do is that I will use the restart function to use directly the result from the previous CFD analysis. So I will not need to compute every time the flow. I will compute directly only the particles every time, so it's very convenient and it will be much faster. For example, if I want to change the diameter of the particles, I will run only the particle analysis rather than running the fluid and the particle together. So now that I've done that, I have to go in the advanced module, and here you see that you have this particle analysis, so you have to activate that. And there's one-way interaction, two-way interaction. So two-way interaction is working only in transient state analysis, so here's it's like that. So one-way interaction of the particle. Two-way interaction means that the particle will interact with the flow, basically. Here in one-way interaction, particle will just follow the flow but will have no impact on the flow. So let's choose that. Now in the field definition, on the bottom you have the initial distribution of the particles so that I created, so you have to select it and then go in the module data, and here you have particle analysis, so you have to define the number of steps for the particle. So let's choose 5,000, let's give a bit more steps, And let's choose an auto increment of, okay, this is auto increment, it's okay. And for the drag force, we'll just use the Stokes, so all that is okay. And we can run that. So same, we just have to wait a bit, but this time it will be much faster because it's not computing the flow. So as you see, it's very fast and it's already finished, and I get the particles like that. So if a particle is falling down up to this position, so the reason that the particle stopped here is that because the size I gave to the particle is too small, and the software automatically reduce the particle dt when the computation. So particle dt is very small, and if I really want to compute the particle with this size, I will need much more step than that. So rather than increasing the number of steps, what I'll do is that I just come back to CFD boundary conditions, particle distribution, and here I will just increase the sphere radius of one order, so it will be like that, and we just have to run again to see what happened. Now it's very fast, and it computed everything. So let's look what we have. So you see it's much faster. So now the particles are really flowing from the inlet to the outlet. Now let's increase another time the size of the particle to see what happened. So I will increase of 0.0002 millimeter, so 0.2 millimeter, and let's run again. Okay, let's look at the results. So particles are flowing, and now what you see is that particles are simply, they are not bouncing against this or the outlet, but they are sticking to this wall. So they are basically depositing against this wall. And this is all for this tutorial. Thank you very much for watching.